Hi. First, I would just like to say I hope you are all doing well in quarantine. I know that personally I am going a little stir crazy, but it is nice to have these opportunities to keep us occupied during this time. So thank you. Now, how have any of you ever wondered what science goes on in your refrigerator to keep your food cool? Well, in most refrigerators, they use what is called the Seebeck effect. The Seebeck effect was discovered in 1918 by the man for whom it was named for, Thomas Seebeck, in 1918. Seebeck found that when you take two dissimilar metal wires, so two different metal wires, and connect them at the ends to create two junctions, and then create a temperature difference between those two junctions, it'll create an electric current. Later on in the 1920s, a man named Peltier added on to Seebeck's effect, saying that if you take those same two dissimilar metal wires, and instead of introducing a temperature difference, but introduced an electric current, it would create a temperature difference. So the way that we measure the voltage produced by thermocouples is by using what's called the Seebeck coefficient, which is the change in voltage of the thermocouples junctions over the change in temperature. And the Seebeck coefficient actually changes depending on the thermocouple you are using. For example, I used a type K thermocouple because it has the highest temperature rating of all thermocouples, and it also has a high Seebeck coefficient. So it creates more voltage per degree increase in temperature difference. Basically, I took the hot junction, the measuring junction, if you will, and I put that in various environments, such as a refrigerator, a freezer, ice water, my oven, kind of some common household appliances. Now, my hypothesis was that as the temperature difference between the hot and cold junction increased, the potential difference of the thermocouple would also increase. This is based off of pretty much all previous studies done with thermocouples and of all current knowledge we have of how thermocouples work. Basically, I took my thermocouple and I measured the room temperature that I was in, and then I used a Type K thermocouple calculator on Fluke Calibration's website to calculate what the potential difference for room temperature would be if the reference junction, the cold junction, were at 0 degrees. I then took my meter readings, which is just the direct millivolt reading from whatever environment I put my measuring junction, or the hot junction, into. I then combined my room temperature potential difference and my meter reading to find what the potential difference should be at the junction with the temperature around it. I then used that junction potential difference to calculate what temperature the junction should be at, and then I could compare that to what the actual temperature of the environment was. Now, I did find that I had some pretty high percent errors, which could be caused by, well, one main cause would be because my multimeter did not read to the thousandth place in decimals for either millivolt readings or temperature readings, which in this case, a thousandth degree change in temperature or a thousandth of a millivolt change can cause very large changes in the overall data, which can account for my high readings because I was missing that crucial decimal place just due to the multimeter I was using. And while I didn't find anything new or spectacular, this type of research is important because it helps verify and solidify what we already know about these topics and confirm previous theories and current knowledge. Thermocouples have a lot of use in modern society, I believe. especially with all the research into green energy, sustainable energy. The fact that you can create energy from heat is very applicable to modern day science.